Let's move into Chapter 4 in the atom. First of all, let's make sure that you know the proton, electron, neutron characteristics and their location within the atom. I have a visual here. Let's take that busy background away. There we go. The proton is positive with a mass of 1 atomic mass unit. That's 1.6 times 10 to the minus 27 grams is what an AMU is worth. That sits inside the nucleus. And so here you see the pluses, those are the protons. The red neutrons are neutral with a charge of 0 here. They're sitting in the nucleus. And this is really exaggerated. The nucleus is much, much smaller relative to the size of the atom than is shown here in this picture. So we're talking 4 powers of 10 difference in size between the nucleus and the total atom size. Then we say the electrons, which are negative, which are approximately 1/1800ths of the size of the neutron and proton. They're negative and they fly on the outside. So basically think about the nucleus as a little tiny positive dense core, and the smear or cloud of electrons flies rapidly around it. Number 17, know these scientists and what they contributed. Alright, so you should know that Dalton is, in the 1800s, he's the English school teacher who brought us back to the basic idea of the atom being the fundamental building block of matter, and that these atoms are being retained in their identity, and they can combine in different combinations with other atoms, and they all have a characteristic mass. So he came up with a lot of fundamental ideas that held true, and over time we saw definition came to the inside of the atom, but Dalton did amazing work in the 1800s with setting us up with a good framework. So J.J. Thomson, he discovered the electron, and he used cathode ray tubes to do that. Ernest Rutherford ran the famous gold foil experiment, and through that he found the nucleus and the proton. Ernest Rutherford's also famous for being the first scientist to find the radioactive particles, alpha, beta, gamma particles. Niels Bohr, he adds definition to the electron locations in the atom, and he sees them as traveling around the nucleus in orbits, and he comes up with the idea of different energy levels for the electrons. Then we come over to Max Planck. Max Planck is the beginning of the quantum model of the atom, which is our current working model. But he's saying that these energy levels for the electrons are quantum jumps that the electron makes, and he also attributes the fact that there are these different energy levels to the wave-like properties of the electron, and that there are certain sweet spots where they exist, and these become the energy levels. And then Werner Heisenberg is listed in your chapter, and there are more than these, but Werner Heisenberg has the uncertainty principle, but frees us up to think about the fact that the electrons are in orbitals, okay, and that becomes an important word. An orbital is this probability region in which the electron exists, and that's our modern thinking, is that the electrons are in specific orbitals around the nucleus. We'll get into that more in a moment. Alright, let's go into the electromagnetic spectrum, and I have an image for this. Okay, this is the electromagnetic spectrum, and a characteristic of the electromagnetic spectrum is that the fundamental particle is the photon, which is a massless bundle of energy, and the photon travels at the speed of light. Which is 3 times 10 to the 8th meters per second. There are different sections of the electromagnetic spectrum that are familiar. You should know these. Radio waves have long wavelengths, and low frequencies, microwaves, infrared radiation. Visible light is this narrow band of, and know this also, for, let's see, it goes this way, 700 to 400 nanometers is the wavelength range of the visible region. Ultraviolet radiation, X-rays, and gamma rays. All of these types of radiation are composed of photons that travel at the same speed. However, the wavelengths change and the frequencies change. Wavelengths and frequencies are related to c, the speed of light, as the speed of light is the wavelength times the frequency. This is wavelength. Measured in meters. And this is frequency. Measured in hertz or per second. So the speed of light is the wavelength times the frequency. Since c is constant, if wavelength gets big, frequency must get small. If wavelength gets small, frequency must grow large. So when you look at the electromagnetic spectrum, everything travels at the same speed, but down here we have the long wavelengths, okay, shown here, long wavelengths, short wavelengths. So this is low frequency, high frequency. Frequency is the number of wavelengths that pass in a second. So more wavelengths can get through in a second if the wavelengths are small. So the low frequency ends up being associated with low energy. Frequency is what's directly related to energy. High frequency is associated with high energy. So in the electromagnetic spectrum, we see gamma rays, which is what we think of as radiation treatment for cancer, or what would be coming off of an atomic bomb. That's high energy and destructive. But radio waves, down here on the low end, are low energy and safe. Visible light is in the middle. And so please familiarize yourself with the electromagnetic spectrum. You have conceptual questions about it, no math, but you should be familiar with the wavelength range of the visible light region, and notice that we're Roy G. Biv this way, and the violet is at the high end in the short wavelength range. Okay, it's violet that has the 400 nanometers, and so violet light is more energetic than red light. Okay, filling out this table, I don't expect you to know anything in particular other than 400 to 700 nanometers here. These are about a meter in length, and then gamma rays would be on these are less than a nanometer in length. Okay, frequency-wise, these are really high, like 10 to the 19th hertz, and radio waves are very low, so it might be 10 to the 9 hertz, something like that. So this is high energy, and this is low energy. And remember, they all travel at the same speed. All right, the fundamental radiation particle of the electromagnetic spectrum is, I'm sure that's been emphasized, photon. Which of the following colors of lights has the highest energy? The violet. The longest wavelength? The red. The highest frequency? The violet. Slowest speed? Trick question. They all travel at the speed of light, C. J.J. Thomson discovered the first subatomic particle to be an electron by using cathode ray tubes. Ernest Rutherford performed the famous gold foil experiment, and two conclusions of this experiment are that atoms are mostly empty space, and a small, dense nucleus contains positive protons. Number 23. What element has the electron configuration of this? 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. We must have a periodic table to do this. So let's bring up a periodic table and let's orient ourselves with how we figure out electron configurations using a periodic table. I really recommend that you do it this way. Alright, first up, you need to know your zones. This is the S zone, this is the P zone, this is the D zone, this is the F zone down on the bottom. The S zone is 2 columns wide. That's because you can only fit 2 electrons into S. The P zone, we have Px, Py, Pz as their 3 orbitals. It's 6 wide. 1, 2, 3, 4, 5, 6. The D zone is 10 columns wide. It ends right here. Count these. You'll see there are 10. And you can fit 10 electrons into the D orbitals, and F's are 14. We won't even bother with going into the F's, so don't worry about that. Alright, you also need to be cognizant of the energy levels. They are the row numbers, and we have 7 energy levels indicated on the table. And so the periodic law of the elements is that atoms build up from the simplest atom, hydrogen. And so we always start filling our electrons in 1s. It's the preferred orbital for all electrons because they're negative, and 1s is closest to the positive nucleus, and that's a nice place to be. The problem is 1s is full with just 2 electrons. And so after that's full, we need to move out to the higher energy level, 2. And electrons always prefer to be at 2s, which is a slightly lower energy level than 2p. And then once 2s and 2p are full, with 2 in 2s and 6 in 2p, we move into the third energy shell, and there we would first fill 3s, then we would fill 3p, and there are 3ds, but it just so happens that 4s's are lower energy than the 3ds. So you need to teach yourself, when you use this method to figure out electron configuration, is to step back an energy level. So when you're going left to right with the periodic table to get electron configurations, you need to say 4s2, and then this is 3ds filling. And then this brings us to our element of interest, which is our electron configuration, which finishes 3d4, so it leads us right to chromium. Okay, so let's go through using the periodic table to figure out how that electron configuration came to be. So we go 1s, 2, okay, and really you could think about helium could rightfully be placed right here because it really has no p electrons. It's written on the right hand side because it's a noble gas. It's an inert gas. Alright, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1, 2, 3, 4. That's where the electron configuration came from. I recommend sit with a periodic table, practice some electron configurations that are shown in your textbook, and verify this method. It works really well. You'll always have it available to you because you'll always have a periodic table. And become proficient with this before the midterm. Alright, so we're going to say, this is chromium. Which ion is isoelectronic with argon? Well, what does isoelectronic mean? This means it has the exact same electron configuration as argon. What is an ion? An ion has a charge. So there are lots of different ions that could be isoelectronic with argon. Let's figure out one of these. Let's first of all figure argon's electron configuration. It would end with, put these back up, 3s2, 3p6. So it is 1s2, 2s2, 2p6, 3s2, 3p6. Well, here are some possibilities. Chloride ion would be Cl-. Chlorine ends with 3p5. But if I had Cl-, it has one extra electron and it would be identical in its electron configuration to argon. It's not argon because it doesn't have the same number of protons in the nucleus. And remember, it's proton count that determines identity. Here's another possibility of something that would be isoelectronic with argon, and that would be sulfur with a 2- charge. Sulfur is sitting there with 1s2, 2s2, 2p6, 3s2, 3p4, but add 2 extras and it's isoelectronic with argon. Well, let's go down. If we look at potassium existing as K+, it would also be isoelectronic with argon. By losing 4s1 electron, we have backed up into the noble gas configuration. And this is really why we find that ions exist in a stable form. K+ is more stable than K. K is highly reactive because metals give away electrons and are more stable with a noble gas equivalent electron configuration than they are as a full atom. And so ions form to gain stability, and we find that nonmetals over here on the right become anions to get to the stable noble gas-like configuration. But on the left of the table, you've got the metals, and metals become cations. In their attempt to become more stable, they'll lose this outermost shell and go backwards to attain a noble gas configuration. Okay, number 25, what is the electron configuration for N3-? That's called nitride ion, and we see nitrogen sitting right here. If nitrogen has 3 extra electrons, it is the equivalent of neon. So that's our answer. We would say neon. If you use brackets like this, it's understood to be 1s2, 2s2, 2p6, the electron configuration of neon. Some of our answers here were K+, Cl-, S2-, and we said this was chromium. Compare and contrast these terms. Orbit, this is like the planet around the sun. This is what Niels Bohr thought electrons went in circular orbits around the nucleus. That's outdated thinking. Orbital is our probability region. I've already stated that. Probability region in which electron resides. We don't know exactly where the electrons are, so we talk in terms of probabilities. Sublevels. These terms can be confusing. I'll change color. Sublevel is S, P, D, F. Those are our sublevels. Energy levels are the rows on the periodic table. Principal energy levels, these are the same. These are equal concepts. So we say energy levels or principal energy levels are the 7 rows of the periodic table. So let's use those terms. How many orbitals are in the third energy level? Well, you can have 3s, and you can have 3p, and you can have 3d. And in 3d, you have 5 orbitals. In 3p, you would have 3, and in 3s, you would have 1. So the answer to this is you would have 9 orbitals. Every orbital can hold 2 electrons, so that would be a total of 18 electrons could exist at maximum capacity of the third energy level. How many sublevels? Okay, this is SPDF. How many sublevels are in the third energy levels? There are 3. You have S, P, and D. What is the difference between an isotope? An isotope is same number protons, different number neutrons. An ion is a charged atom. So let's give an example of each of these. Isotopes would be carbon 12. Carbon always has 6 protons, but it could have a different number of neutrons, so it could be carbon 12, or the familiar carbon 14, which is used for carbon 14 dating, has a couple extra neutrons in it. Versus a charged atom or an ion would be like potassium ion, K+. Alright, this is where we lose an electron. Plus or minus electrons is how the ions come to be. Changing neutron count is what causes the isotope to form. Clear this off. Let's scroll this. Calculate the average atomic mass of magnesium given the following data for the natural isotopes. Alright, so this just takes a little bit of practice. You need to use a weighted average method. Turn these percents into decimal equivalents, 0.7870. Okay, so use the more accurate mass times that percentage plus this mass times this percentage plus this mass times this percentage to get the weighted average. So we would do 23.985 24.310 AMU. I'm sticking with the sig figs. We get 4, so I guess we wouldn't say that. Does that seem reasonable? It does. It's most like this one. Most of them are that mass.